So again, expectation is the average, what you would expect to happen, and our formula for finding the expectation of something is just multiplying each event by its probabilities and adding them up. So for this example, if we looked at rolling a die once, you would have the possibilities 1, 2, 3, 4, 5, and 6, and we could make a probability distribution chart of that. And each of the probabilities would be 1 out of 6. Now, if we multiply each event by its probability and add those all up, you're going to get 21 out of 6, or an average of 3.5. Which makes sense, because if you think of the numbers 1 through 6, what happens right in the middle of all of those numbers is 3.5. So this is using the formula of multiplying each event by its probability and adding it up. Now you could also think about this one theoretically, without using the formula, and say, well, theoretically, if I roll a die 6 times, and in theory I get each number once, then I'll get the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6. I'll get all the numbers once in 6 tries. And if I want to find an average, and my values were 1, 2, 3, 4, 5, and 6, I would just have to add those things up and then divide by 6. And if you add 1 plus 2 plus 3 plus 4 plus 5 plus 6 together, you get 21. Divide that by the 6 times, and you find out your average is 3.5 as well. So some of these questions, you can think about them and create an actual situation and find out the average, or you can use the formula and say each event times by its probability to figure it out. So here's one for you to try. If you're not quite ready, don't look up, but once you are ready, you can take a peek at how you did. All right, so there's the actual answer. So now we'll get into some questions that don't give us numbers. The random variable x can take only the values 1, 2, and 3, and it tells us a relationship. 1 and 2 have equal probability, and the 3 is 3 times as likely. So values 1 and 2 are equally likely. So we can draw a probability distribution, and we can start by just putting in a variable for what we don't know. Now, why wouldn't I use the variable x? Why did I chose k. I could have chosen another letter, but why would x be a bad choice? Yeah, we're already using it here. Now, in the IB course, and especially when you get into writing your papers, they're very particular. If you use something to represent something early, later on, you shouldn't use that variable again. You've already said, I'm going to let x equal this. Then for your entire paper, that's what x is. As soon as you come to something else that's new, you're going to have to define a new variable. So one of the things that you'll be looking at in your papers is how do we define things clearly so everything has its own thing that it means as you go through. So the problem here, in order to find the expectation, yes? Oh, and mine says 3 times. Okay. Well, change yours to 3, because then we'll do it the same. So with these values, before we can find the expectation, we have to find the value of k. How can we do that? Well, we know that that bottom part always adds up to equal 1. And so solving for k gives us 1/5, and then once you have that, then you can find the expectation. Here we go. And here is example 3, take 3. All right, so, yeah. There we go. You guys are so... Okay, so now this is either we're dealing with, you know, you guys are so polite and you don't want to say when there's a mistake up on the board, or maybe we have some serious math confidence issues in the room, and like, oh, I got 39 out of 30. So there's our probability distribution. So it's a matter of deciphering what this means. Probability x equals x, well, that's the bottom of our distribution, is going to equal x over k. So for 1, it's going to be 1 over k. For 2, it's going to be 2 over k, and so on. Currently, we don't know what k is, but since that has to add up to 1, we can solve for k. And then our expectation is easy to figure out. Now, when making your probability distribution chart, there's 2 ways to look at this. You could look at this with the values that are given and find out what you would expect to win or lose from this spinner, and then take the $5 off at the end. Or you could take the $5 off right away, saying if I spin a 15, I'm only going to win $10, right? Because I spent 5 already to play. If I spin the 10, I'm only going to win $5 because I've already spent 5 to play, and -4 and -14. Then if we do the expected value from here, we're going to get -3 over 4, or we're going to expect to lose 75 cents. Now, part of why, again, I like this game is I think the mathematics that are there are somewhat a little bit deceiving to the person that's playing. As soon as you pay your $5, you've forgotten about paying the $5. A lot of people do this when they play a game. They're like, I forgot I paid $5. Look, you can win on this chart $26 and only lose 9. It's a good thing to play, because your winning things are better than your losing. And also, when you spin, it appears that you win more times than you lose, because you have 3 places that are positive and only 1 place that's negative. Even though that $1 winning, if you remember, oh, I paid $5 for that loonie, maybe that's not such a good deal. But it appears in this game like, oh, I can win more times than I lose, and my winning ones are bigger than my losing ones. Because you go, your mind might even play tricks on you and say, okay, even if I lose $9 plus my 5, I'm only losing 14, but there I win 15. But you forgot you spent 5. So I think this game is a little bit creative in that it might be convincing to play, but if I got you to play 100 times, I should expect to win $75. Don't know if that's quite worthwhile setting up a little thing in the hallway at lunch hour. Probably wouldn't go over well.